Hello everyone, welcome to the video. In this video, we are going to see how to design a transistor switch. So, in this switch design, there are two kinds of ways in which you can design a switch. One is called high side switching. In the case of high side switching, the load is connected between the collector and the ground node, and a PNP transistor is used. While in the case of a low side switching, the load is connected between the VCC and the collector of the transistor, and an NPN transistor is used in this case. So we have designed for the purpose of our demonstration, we are designing a LDR circuit. LDR means light dependent resistor. It is a resistor whose resistance changes with the light intensity. So here, if you see, R1 is a fixed resistor that we are using in the circuit, and R2 is the LDR resistance. So the LDR resistance, when there is light, it is the resistance goes low, and when it is when it is dark, the resistance increases to a higher value. So typically 2500 ohms is a value when the light is glowing, and when it is dark, the resistance can go over 10 kilo ohms. So we are using 9 volt as a battery power supply in this circuit, and 2N2907 a transistor is used as a PNP transistor here. So this is the case of high side switching. And in order to limit the current through the LED, we have connected an LED to this circuit. So what the circuit does is, when the light goes out, the LED starts glowing, and when it is bright and the outside light is glowing, the LED turns off. This is the purpose of the circuit. In order to limit the current through this LED, we are using 440 ohm resistor. So let's see how to use the transistor as a switch. So these are the parameters for which are used as specifications for designing the circuit. So first we have to decide what is the switching voltage. So switching voltage is given by 9 volt minus zero point 0.7 volt, which is the voltage at the base. So this zero point 0.7 volt is actually the voltage across the base emitter diode. So this comes to around 8.3 volts. Then if we calculate voltage at the base, we have to find the voltage at this point, which is given by the voltage divider rule. So this is if we substitute the values in the equation for the voltage divider and solve for the values, then we get 8.3 volts is equal to 9 volts times R1 by R1 plus RLDR. So when we substitute the values inside this, we get that RLDR should be 11.8, 1 by 11.8 times R1, which is equal to 2796 ohms. So in this case, when the LDR resistance is 2500 ohms, the transistor will be in switched off condition, because for the transistor to turn on, we need the resistance of the LDR to be at least 2796 ohms. Any value greater than this would turn on the transistor, and current would flow in this direction into the LED, and then the LED would start glowing. So this is how we calculate the turn on voltage for the circuit. Let's now see how to calculate the base resistor value. So in order to calculate the base resistor value, the first step is to determine the maximum collector current. So in order to calculate the collector current at saturation, we need to find VCC minus VCE sat minus VLED divided by R. This VLED is the voltage across the LED, which comes to around zero point 0.7 to zero point 0.8 volts. And then VCE sat is the voltage between the collector and emitter terminals when the transistor is on. This voltage is typically zero point 0.2 to zero point 0.3 volts. We are assuming zero point 0.3 volts in this case. So when we calculate 9 minus zero point 0.3 minus zero point 0.8 divided by the current limiting resistor R, which is equal to 440 ohms, we get a IC sat maximum collector current value of 17.9 milliamps. Then in order to keep the transistor in saturation, we need to choose a forced beta value of 10. Forced beta here is HFE. We can find it from the data sheet. For the since uh, we want the transistor to operate in the cutoff and saturation regions, we are choosing this HFE of 10. Typically, in the active region of the transistor output characteristic, we would have a beta of 100 or 200. But since this is saturation, we are choosing a beta of 10. Then we calculate the minimum base current by finding IC sat by forced beta. This is equal to 17.95 milliamp divided by 10, which is 1.795 milliamps. Then in order to provide a safety, so whatever we are doing here is for hard saturation. Even if there is any change in the parameters of the transistor, the design should should be robust enough so that the transistor switches on at the required voltage and switches off at the expected designed voltage. So in order to do that, we are using a safety factor of 2, and then we calculate IB design as 2 times IB min, which is 3.591 milliamps. Finally, we calculate the base resistor value from the equation VCC minus VBE sat by IB. So this is 9 minus zero point 0.7 divided by 3.591 times 10 power minus 3. So this we get from this we get RB as 2.3 kilo ohm, and this is the resistor value that we are using in the circuit. Let us now see how to simulate the circuit on LT Spice. So first we will see how to simulate the high side switching circuit. So we can see here that the 9 volt power source is connected here, and then R2 is the LDR resistance value, R1 is the fixed resistance, R4 with equal to 2.3 kilo ohms is the base resistor value, 440 ohms is the collector resistance, R3. We are using a 2907 transistor here, which is a PNP transistor, and then the load is connected to a LED. So we are going to simulate this, perform a transient analysis for a period of 10 seconds. Let me run the simulation. So let's see the voltage at the collector end of the transistor. So we can see that the voltage is around 788 millivolts. Let's measure the current through the collector. Current is in the microamp range. So I'll show a magnified view of this. So you can see that the voltage is shown in green is 788 millivolts, and the voltage in and the current in blue is 363 microamps. So now we will see what is the voltage and current when the LDR resistance varies. So let's make this around 10K. I'll run the simulation again. Now when we measure the voltage, we get 8.8 volts, which means the transistor is being switched on and the supply voltage is appearing at the uh, load. So let's measure the current through the LED. So we see that we are getting around 18.4 milliamps. So once again, when I show it in the magnified form, we get 8.8 volts at the LED terminal, load terminal, and we get 18 milliamps as the current through the LED. So this is similar to the value that we designed earlier when we calculated using pen and paper. Let us now simulate a low side switching circuit. The difference here in this circuit is that we are having a NPN transistor 2N2222, and the transistor is mirrored. So you see that the emitter is connected to the ground and the collector side has the load. One more difference is that the fixed resistance is moved up. So here it is R2 and R1 is actually the LDR resistance. So let us simulate the circuit for LDR resistance value of 2500 ohms. I'm running a transient analysis for 10 seconds. So let's measure the voltage at the collector terminal of the transistor. So we see that we get around 8.2 volts. So this actually means that the transistor is not switched on. It is turned off presently and the LED doesn't glow. Let's measure the current through the collector. So we are seeing around 350 microamps of current. Let me show you this in the magnified version. So we get 8.2 volts for the collector voltage and 350 microamps for the collector current. So let's alter the value of the LDR resistance to 10K. I'm running the simulation again. Now when we probe the collector voltage, we get 143 millivolts. And the current through the collector is 18 milliamp, which means the transistor is on and a current of 18 milliamps is flowing through the LED. This will make the LED glow. So once again showing the plot in a magnified form, you see that voltage at the collector is 143 millivolt and collector current is 18 milliamp.
Let's see a practical application of a transistor used as a switch. So the circuit that I have connected here is a light dependent resistor circuit. A light dependent resistor is a component whose resistance varies with light. So the more light that shines on it, the lesser will be its resistance. When the room is dark, the resistance of the LDR goes up. So here we have connected a 9-volt battery as a power supply. This is the LDR component, and then we have also connected a red colored LED. Behind the LED you see a 2907 transistor, which is actually performing the switching action. It is a PNP transistor. We are using PNP here because we want to um, switch on the light when it is dark. So for that purpose we are using PNP transistor. So let's now see the result now. So when I block the LDR, you can see that the LED turns on. When I withdraw, the LED turns off. Once again, when I block the LDR from the light, LED turns on, and when I withdraw, it turns off. This is how the transistor is working as a switch. I have now disconnected the rest of the circuit and I am measuring the resistance of the LDR when the light is on. So you can see here that it is having 7.4 kilo ohms, and when I try to block the LDR of the light, it is having around 18 to 19 kilo.
Hope you had a clear understanding of the circuit from the practical demonstration. So we can use the LDR to turn on, we can use the transistor as a switch to both turn on the LED when the light is present or when it is dark. That depends on how the circuit is connected. In both NPN and PNP transistor, we can use this logic. One final point to note is that this 33K resistor was derived from by using a potentiometer initially, and instead of the 33K fixed resistor, you can use a variable resistor to adjust the sensitivity of the circuit. So finally, I would like to thank Google's AI search mode to helping me design the circuit. Thank you for watching the video.